Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on control systems theory. Today we are going to continue our discussion on root locus technique. Last time we started the discussion on the 10 rules of root locus, and so far we have discussed 6 of the rules. So rule number 1 of root locus is that root locus originates at the open loop poles. So this means that when you close the loop and your control gain is very low or close to 0, then closed loop system and the open loop system have the poles at pretty much the same location. And then root locus terminates at the open loop zeros. So this means that when you close the loop and your gain is a very high value, very close to infinite value, then your closed loop poles are very close to the location of your open loop zeros. Then we studied that number of branches in the root locus is equal to the number of open loop poles, which means that every pole in the root locus, every open loop pole follows its own path in the root locus. Similarly, we found that asymptotes in the root locus are calculated using this angle. So what are asymptotes? Asymptotes are those paths of those poles who cannot find any zero to converge to. You already know that in a causal system, a number of zeros is less than or equal to number of poles. So if the number of zeros is less than the number of poles, so some of the poles will not find corresponding zeros to which they go as the gain is increased in the feedback loop. So those poles go to infinity. And which path they take in order to go to infinity? If there is only one excessive pole, it goes at the angle of minus 180 degree. If there are two excessive poles, one goes at 90 degree, another goes at 270 degree. If there are three excessive poles, one goes at 60 degree, other goes at minus 60 degree, and the third one goes at 180 degree, and so on. So we did this in the last lecture. We looked at some examples of asymptotes for the difference between poles and zeros up to 4. Okay, so the next rule that we studied last time was that the centroid point or center of gravity, you can call it center of gravity or you can call it the intersection point of the asymptotes on the real axis. This is calculated by using sum of all pole locations minus sum of all zero locations divided by the relative difference between poles and zeros. We also looked at the examples of calculating sigma 1 in the last lecture. Root locus exists on real axis if the number of poles and zeros to the right side of a test point is odd. So this is rule number 6, and we have already looked at the examples related to this rule, and now we are going to continue on towards the rule number 7. Rule number 7 of root locus says that angle of departure for a pole or angle of arrival at a zero. So how do we calculate that? That's rule number 7. What is an angle of departure? So you already know that in the beginning closed loop poles are at the same location as the open loop poles. As we start to increase the gain of the root locus, which you can think of as the gain of the controller, as we start increasing that gain, the poles change location. So at what angle they move from their original location? So if there's a pole here, does it go like this? If there's a pole here, does it go like this? As we increase the gain, does it go this way? Which way it goes? And then similarly, when the gain is very high, the poles have to reach some open loop zero or maybe infinity. So at what angle? We already have looked at the angles at which pole reach infinity. Those are called asymptotes. So in this rule we will look at the angles at which poles arrive at the zeros. So luckily the formula for calculating the angle of arrival is exactly the same as the formula for calculating the angle of departure. So we use the angle condition. with the test point infinitesimally. So what we do is, if we have to calculate the angle of departure of a pole, we put a test point S1 very close to that pole, and if we have to calculate the angle of arrival at a zero, we put a test point very close to that zero, infinitesimally close. So infinitesimally close means that the distance between that zero or pole and the test point is so small that it cannot it has almost no magnitude. The angle between the pole 0 in question and the test point shall be the only unknown. So this will become clear with the help of this diagram. So for example, let us suppose we have this like 5 poles and 1 0 in a system. This is let's say open loop system having 5 poles and a 0, and we want to calculate the angle of departure of this pole. So if we want to calculate the angle of departure of this pole, we put a test point S1 very close to this pole, and then we draw the vectors and calculate the angles as we did in the first part of root locus lecture. And we also imagine a line between this pole P4 and the test point S1. So S1 is so close to P4 that we don't know whether it is on the right side of P4 or on the left side of P4. Here in the diagram, you may say that the S1 is on the left side of P4, but this is just to show you that S1 is there. But in theory, S1 is so close to this pole that we don't know in which direction it is. So the angle of P4 to S1, that is unknown, and that we will find using the angle condition. So angle condition says that sum of angles of all the zeros minus sum of angles of all the poles is 2k plus 1 pi. For convenience, we can put k equals 0 here, and then we can calculate the angles. So these angles we can actually calculate because we know this location and we know the S1 location, and this becomes a triangle. So we can find the angle of a triangle by tangent inverse. So we know what is the perpendicular distance and what is the horizontal distance. So tangent inverse of perpendicular over base, that would be theta. So so here we calculate this angle theta z1, and since there are no other zeros, so sum of angle of zeros minus sum of angle of all poles. There are 5 poles, so each pole has an angle. The special thing is that we can calculate theta p1, theta p2, theta p3, theta p5, but theta p4 is unknown. That we will calculate using this equation. So we will put k equals 0, and the only unknown in this equation will be theta p4, and that we will calculate. So I can give you an example of this. So for example, I have copied the same diagram onto the next slide. So we have theta p4 unknown here. So let's put in some locations. So let us assume that this pole is at -1, and this pole p5 is at -2, like this is -2j vertically and -2 horizontally. So -2 let us assume that this p4 is the complex conjugate of p5, and then p2 is -4 plus j. -4 means that it is the horizontal distance is -4 and the vertical distance is 1. So p3 is complex conjugate of p2, and z1 is at -2 location. So then what happens is that if you calculate the theta by tangent inverse of perpendicular, so you can see that the horizontal distance between this pole and this test point is, this pole is at -4, test point is at -2. So there is the horizontal distance is 2 and the vertical distance is 1, because this is at 2j and this is at 1j. So vertical distance is 1. So tangent inverse 1/2, that would be the angle, and that you can find like it's written here. So tangent inverse 1/2 is 0.4636 radians. You can also verify these angles using calculator, and so we calculate all the angles except for theta p4, and then we can calculate theta p4 using the angle condition. All right, so uh, next what we do is we plug in all the values. This is the value of theta z1 minus the value of all the angles of the poles except for the theta p4, and on the other side we put k equals 0, so 2k plus 1 into pi becomes simple pi. And when we solve this equation to find theta p4, we find that theta p4 is 0.6626 radians, which is equal to 37.96 degrees. So if this is 37.96 degrees, that means that with respect to positive x-axis, this angle will start moving at this pole will start moving at an angle of 40 degrees with respect to positive axis. So we know now that as we start to increase the gain of root locus, this particular pole will start moving at an angle of 40 degree with respect to real axis. So this pole will start going this way. So we know that which way this pole will start to move. So since root locus is symmetric with respect to real axis, if this pole is going at 40 degrees with the real axis, this pole will automatically, we don't have to calculate the angle of departure of this pole will automatically be going at a negative 40 degrees or negative 37.96 degrees. So this pole will have like this type of angle of departure, and this pole will have this type of angle of departure. So this was the angle of departure. Similarly, we can put this test point very close to this 0 and can find the angle of arrival at this 0. Whichever pole arrives at this 0, we can find the angle at which this pole will arrive. We can also guess it, because if you remember rule number 6 of root locus, you put a pointer here, you can see that on the right side there is no pole or 0, so there will be no root locus on the real axis here, and here there will be root locus on the real axis. So there is a chance that this pole will go to this 0 as you increase the gain. So angle of arrival of this 0 is, we can guess that it will be 180 degrees, but we can also calculate it using the angle condition, and it will turn out to be 180 degrees. Alright, so this was the example regarding the angle of departure. And then I also explained that if you are working with complex conjugate poles, then if you calculate the angle of departure of one of the poles, the other pole will have the negative of that angle. So you don't have to calculate the angle of departure of both of these poles. You calculate one of them, and similarly for these two complex conjugate poles, just calculate the angle of departure of one of them. And for this pole, you can see from the rule number 6, the angle of departure will be 180 degrees. The angle of arrival of the 0 will be 0 degrees, because the arrival is from the left side of the 0. So it is coming from the positive x-axis side. So arrival will probably be 0 degree, and the departure angle will be 180 degree because it is going to the right side. So this pole is departing at an angle of 180 degree and arriving to the 0 at an angle of 0 degrees. But you can also verify this statement by using this method and see what angle of departure and angle of arrival turn out to be. Similarly, the next rule is find the intersection of root locus with j omega axis. So some root locus cut the j omega axis. So this is the j omega axis. This axis is the j omega axis. If the path of any pole cut this j omega axis or passes through this j omega axis, how do we know the exact point at j omega axis through which the path of the pole goes? So this is rule number 8. So how do we do this? We basically use the Routh-Hurwitz stability criteria for this on the closed loop characteristic polynomial. So this point is a little bit elaborated, like a little bit complex to calculate the intersection point of root locus on with j omega axis, because we have to do the whole Routh-Hurwitz table for this. So let us look at an example. For example, let us assume that we have an open loop system where this is the root locus gain k, and this open loop system has 1 0 at s equal -2, a pole at -1. So this is the equation for this system. So this system, this system has poles at these locations, and if you find the corresponding polynomials, then this basically is the same system as in the previous example. So this is the open loop transfer function. The corresponding closed loop transfer function you already know how to find. If you calculate the corresponding closed loop transfer function, this will be numerator divided by denominator plus numerator. So we have already discussed this multiple times in previous lectures. Closed loop characteristic polynomial shall be this one. So if I multiply everything out, then the closed loop characteristic polynomial will become something like this. Okay, so now I have the closed loop characteristic polynomial. So we can apply Routh-Hurwitz on this called closed loop characteristic polynomial and see the value of k for which poles lie on the j omega axis. So usually we use Routh-Hurwitz to find whether the poles are in open left half plane or not. But if you remember, there are some special cases in Routh-Hurwitz, especially the special case 2 where the whole row is 0. In that special case, usually there comes a condition where there are poles on the j omega axis. And you also have to remember, not every root locus passes through j omega axis. So when you apply Routh-Hurwitz, sometimes there will be no value of k for which the roots will lie on the j omega axis, and in that case, after your calculations, you can conclude that the poles do not cross j omega axis at all. But in this example, so we already know how to construct the Routh-Hurwitz table. There is a row for every power of s, and we know how to fill in these rows. We put in coefficient of s to the power 5, and then we leave s to the power 4 and put the next coefficient, leave 1 and put the next. And similarly we fill in the next row, and then we calculate 13 into 69 minus 189 divided by 13, that would be a. And then we can calculate 13 into 268 plus k minus 1 into 2k plus 136 divided by 13, that would be b, and so on. We keep on filling out this table, and you already know how to do that. Once the table is complete, now we look at the values of a, b, c, d and see what are the ways of making a row in this table equal to 0 and forming the auxiliary equation, and see we will see if the roots of the auxiliary equation are on the j omega axis or not. So a, we already know, 13 into 69 minus 189 divided by 13, that would be 54.46. b would be 13 into 268 plus k minus 1 into 2k plus 136, here it is, divided by 13, that will simplify out to this value. And then c will be something like this. So c is a into 189, which is 54.46 into 189, and in minus 13 into b is this whole thing, and then divided by a. When you do all the simplification, it turns out to be like. Alright, so next we look at the value of d. d would be c into b minus a into 2k plus 136 divided by c, and if you calculate this and simplify this, this will be this whole expression minus this whole expression. So d is quite complicated, but we can deal with that. So we have all a, b, c, d listed out here, and now the task is to make a row 0. So this row looks easy. So if we try to make this row equal to 0, then what we have is let us see. So I'll just copy this whole thing into the next slide. This is the table. These are the values of a, b, c, d. Now the trick is to find the value of k that makes the whole row of zeros, and then see if the roots of auxiliary equation lie on j omega axis or not. This is the whole trick of finding out the intersection of root locus with the j omega axis. Excuse me. So So last row becomes 0 for k is equal to minus 68. If we put k is equal to minus 68, then 2k plus 136 becomes 0. But negative value of k is out of scope. We are only going to study the gain of root locus to be between 0 and infinity. So we will not make this row equal to 0. So next choice is that we can make this whole row equal to 0 by making d equal 0. And if you solve this whole expression, if you put this whole expression equal to 0, take the LCM and remove the denominator and simplify everything, then you will see that for k equal 478, the d becomes 0. So we will use, since this is a positive value, we will use this value, k is equal to 478. And next what we will do is, for k equal 478, this row whole row becomes 0, and this row forms the auxiliary equation. When we form the auxiliary equation using this row, we have to put k equal to 478, because that is the value of k which achieves 0 row. So when we put k is equal to 478 and form the auxiliary equation, the auxiliary equation turns out to be 31s square plus 1092, which gives the following roots. So these roots are 0 plus 5.93j and 0 minus 5.93j, so which is actually on the j omega axis. This means that our root locus of this of the transfer function, for which we have done this all closed loop analysis, this the root locus of this open loop transfer function will pass through the j omega axis at these 2 points. So remember, root locus is symmetric with respect to real axis. So if one of the pole passes through real axis on a non-zero value, passes through the j omega axis on the non-zero value, another pole to keep the symmetry will pass through the negative of that value. So we can see pictorially here that this is the diagram of the poles and zeros of the system that we considered, and these poles we already calculated the angle of departure, that is around 40 degree. So the angle of departure of this pole, it will be around minus 40 degree. And since there is like excess of like 5 poles and 1 0, we already know that the asymptotes will be at 45 degree. So this pole will bend slightly towards upward to make the angle 45 degrees. So this angle with the final angle of the path of the pole with the horizontal axis will be 45 degree, but the angle of departure will be 37 point something or 38 degree. So this is how this is going to move, and when it is crossing the j omega axis, it will be at 5.93j, or you can say roughly 6j. And similarly this will be minus 5.93j or roughly minus 6j. So this is minus 6j and this is plus 6j on the j omega axis. So root locus will intersect the j omega axis at these 2 points, and you can see that the path of this pole is the mirror image of the path of this pole. So root locus is symmetric with respect to real axis. So this was about the intersection of root locus on j omega axis. This I have also indicated you by putting small circles here, that this is the intersections, these are the intersections. The next is find the breakaway or break-in points. So this is the rule number 9 of root locus, that calculation of breakaway points or break-in points. So before I go into the calculation, I have to demonstrate what is a breakaway point and what is a break-in point. So I have put in 2 examples. First example is that there are 2 poles and their root locus is such that when this is the open loop location of the pole, this is the open loop location. When you start to increase the gain, this pole moves this way and this pole moves this way. And when both of these poles meet in the middle, and when they meet, they break away. So breakaway is always like one pole goes up and the other pole goes down. So path of the pole never overlaps. So whenever it collides, the poles break away. So all the breakaways happen on the real axis. So the rule number 9 is how to calculate this exact point where the poles meet and break away. And similarly, sometimes it happens that there are poles on the complex conjugate poles, or maybe poles could be like away from the real axis, and they are their root locus path is such that they converge onto, whenever a pole will converge onto real axis, due to symmetry around real axis, another pole at the same time will also converge to the real axis. And when these both poles converge to the real axis, they will again break in. Break in means they break into the real axis. So one pole, when this pole reaches at the same gain, this pole also reaches the same point, and one of the poles will go this way and other pole will go this way. This is called break in. So rule number 9 will tell us how to calculate the break-in point. So similar to the angle of arrival and angle of departure, the formula that we use, the mathematics that we use to calculate the breakaway point is the same as for break-in point. So now, how do we calculate breakaway and break-in points? So this is the breakaway point. Similarly, this is the break-in point. So break-in point, breakaway point. So I've also highlighted using the circles. So how do we calculate? So necessary condition for a breakaway or break-in point is that the derivative with respect to s of the open loop transfer function without the gain k is 0. You take the derivative and you put it equal to 0. The solution of this equation will give you breakaway or break-in points. So remember that this is the necessary condition, which means that if this condition is satisfied, then there might be breakaway points or there may not be breakaway points. This calculation will give you the actual breakaway or break-in points only if they exist in the root locus. Sometimes the solution to this equation will be complex. So breakaway points or break-in points are always real. If the solution to this equation is complex, then you already know that there are no breakaway or break-in points in the root locus. Not every root locus has breakaway or break-in points. Similarly, not every root locus has intersection with j omega axis. So example, let us look at this open loop transfer function. And when we take the derivative with respect to s, you already know how to take the derivative of the quotient rule. We apply the quotient rule and take the derivative. This is the derivative. When we put it equal to 0, the solution will be s equal to -4. So we know that for this type of open loop transfer function, one pole is at -3, another pole is at -5, and when they move, they break away at, so this pole, let's say this is at -3, this is at -5, they move, when you increase the gain, this pole moves towards -4, this pole moves towards -4. At -4 they meet and break away from each other. Alright, so this was the discussion on breakaway and break-in point. Next we look at the final and 10th rule of root locus, which is to find the gain of root locus k at any desired point of root locus. So this is easy because we have already looked at the magnitude condition, and magnitude condition give us k equals the product of absolute values of s plus pi divided by the product of absolute values of s plus zi for all the poles and zeros. When we plug in, when we substitute the value of s in this gain magnitude condition with the s1 point, the point at which we want to calculate the gain, then we get the gain value at that point. For example, let us say we want to calculate the gain at some point s1. Then let us say we have this system. This is the same system as we discussed in the previous example when we were calculating the breakaway and break-in point. So this system has two poles and no zero. So denominator will not come into play here. Denominator, when there is no zero, then the denominator is simply 1. So we want to find the gain of this gain of the root locus of this transfer function at point s equal -4. We already know from the slide, the previous slide number 10, that this is the breakaway point. So we want to know the gain of the root locus at which the both poles break away from each other. This point is important because this is a second order system, and when both poles meet each other at point -4, the system will become critically damped. And if we further increase the gain, one pole will go upward and other will go downward, and the system will become underdamped. So this is the point where system shifts from being critically damped to underdamped. So that's why we are interested in finding out the gain. So how do we find out the gain? We just plug in this formula. Absolute value of instead of s we put -4, and the first pole pi is +3, so we put it here +3, and the second one is +5, so we plug in here +5, and instead of s we put -4, and since there are no zeros, the denominator stays 1, and when we calculate these, this turn out to be 1. So this means that when gain is equal to 1, then both of the poles will be at -4 location. We can also confirm that or cross verify this result. How can we cross verify this result? We can calculate the closed loop transfer function. So this is the open loop transfer function, and we can calculate the closed loop transfer function by including the gain of the root locus. This is the closed loop transfer function, and when you simplify the closed loop transfer function, this is the characteristic polynomial of the closed loop transfer function. We can put k equal 1 here and calculate the roots of this equation, and the roots of this equation at k equal 1 should be -4 repeated root. So you can see that when k is equal to 1, the characteristic equation is s square plus 8s plus 16, which is equal to s plus 4 whole square. So s plus 4 whole square, the roots of s plus 4 whole square is -4 twice. So we verify that at gain k equal 1, the poles are at -4, so which was originally what we were looking at. So this completes our discussion on root locus, and at the end I briefly summarize today's lecture. In the last lecture we discussed 6 out of the 10 rules. So remember, this is the third discussion on root locus. In the first discussion we discussed some preliminaries, mathematical preliminaries. Second discussion we discussed the 6 rules of root locus, and here are the 6 rules. Root locus originates at open loop poles, terminates at open loop zeros, number of branches is equal to number of open loop poles, asymptotes are found by this formula, centroid is found by this formula, and root locus exists on real axis if the number of zeros or poles to the right of the test point is odd. Then we looked at 3 of the rules today, 4 rules today. Rule number 7, for angle of departure or arrival, we put a test point very close to the pole or zero for which we want to find the angle of departure or arrival. Then we calculate all the angles, and the only unknown angle is the angle of the pole or zero for which the test point is infinitesimally close. And then we put in a few numbers into this example, and putting in numbers gives us the answer in terms of a number. And then we know that this pole departs at 37.96 degrees, and this pole will depart at -37.96 due to symmetry around the real axis. And then we find the intersection of root locus with j omega axis. We use the same example that we used in the previous rule. And then we looked at the closed loop polynomial. We constructed the Rauther-Hurwitz table, and we made one of the rows to be 0, but in order to make this row 0 we use the positive value of k. We form auxiliary equation. The roots of auxiliary equation are in fact on the j omega axis. It is not necessary that always the roots will be on j omega axis. The roots could be away from j omega axis. If the roots are not on j omega axis, that means that root locus does not intersect j omega axis. But if the roots are on the j omega axis, then it means that the root locus does intersect at these points on the j omega axis. So we saw a graphical depiction of that. And next we moved on to rule number 9. We looked at what is breakaway point, what is break-in point, and we looked at how to calculate breakaway and break-in points. So we this is the derivative of open loop transfer function and put it equal to 0, and then when we solve, this becomes breakaway or break-in point. We have to also look at the actual root locus, apply rule number 6, and if rule number 6 says that there is a root locus on this point on the real axis, only then this will be the actual breakaway or break-in point. If there is no root locus at -4 for this transfer function, then this point is basically a fake point. This point is not counted. So, or if this point is complex, having real and imaginary parts, also then this point is not counted, because all the breakaway break-in points are on the real axis. So this was our example, and finally we looked at how to find the gain of root locus at any point. So we looked at an example, and this was transfer function. We applied the formula. We looked at that the gain equal 1 for at this location of the root locus, and we confirmed that by using the closed loop transfer function. And this completes the discussion about all the 10 rules of root locus. Hope that you were able to understand these concepts. Thank you for watching, and let me know if you have any